Well, good afternoon. Welcome to AP Calculus AB. My name is Mr. Royce. I'll be your instructor for today. We're starting a unit where instead of the problems taking 20 minutes and a full page of work, now we're going to be doing problems that take 20 seconds. And the homework solutions for the homework due on Monday, the solutions all fit on one sheet of paper. It's really a drastic change. We're looking at antiderivatives. When you look at an antiderivative, you're really looking at an inverse derivative. We're taking the derivative process, taking a movie of it, and then we're going to play the movie backwards. We're going to watch this in reverse. So, first of all, let's look at the shapes of these operators. The derivative operator has a commonly referred to in this class as a lima bean shape. Not all derivatives have the lima bean, or not all operators have a lima bean shape. I mean, you're used to operators where they look like a plus sign, where there's two inputs. Inputs are 5 plus 3, and the operation is to add them together. Here, the operator has a lima bean shape, and sometimes you see it as dy dx, but that lima bean shaped operator is still visible. Taking the derivative with respect to x of y, or in this format is just f prime of x, where the operator is expressed as a prime. So there's several ways to write the derivative operator. What's the shape of the operator for antiderivatives? The shape of the operator is, what is that? It kind of looks like a canoe. And the input to the operator is not the function y like this. It's like f of x. It's like here's the input to the operator where we're using the input operator d dx. It's like the main verb. What's the subject? We're applying the derivative operator to the subject of the function y. Well, here's the subject for the antiderivative. We're taking the antiderivative with respect to x, and it looks like an elongated s. It is an elongated s. We're taking the antiderivative with respect to x of what? To what subject will we apply this main verb of taking the antiderivative? It's whatever happens to be in between the elongated s and the dx. We're taking the antiderivative with respect to x of f prime of x. What is the underlying concept, though? We saw several times in our previous unit where when we were going from f prime to f, if we had a derivative like f prime equals something like 2x, we noticed that if we tried to back it up and go back to f, there was an entire family of curves whose derivative is 2x. I can think of many, like x squared plus 5. If f of x is x squared plus 5, the derivative will be 2x. X squared plus 3, the derivative is 2x. X squared minus 1, the derivative is 2x. So when we go backwards, going forwards, by the way, is going from f to f prime, taking the derivative. But when we go backwards from f prime back to f, we're going to lose the vertical shift information. So the antiderivative of 2x is a family of curves. It's x squared plus 5, x squared plus 3, x squared minus 1. In general, it's some function plus an unknown constant. It's an entire family of curves. When you go from f prime to f, that's what the antiderivative does for you. It reverses the derivative process. It starts with the derivative and takes you back to not just an original function, but a whole family of functions. I mean, just off to the side, to make sense of this example, the symbolic representation of this idea is that the antiderivative of 2x with respect to x is the entire family of curves x squared plus some unknown constant. It might be x squared plus 5. It might be x squared plus 3. It might be x squared minus 1. But don't all of these green family members have the same derivative of 2x? Yeah, so the antiderivative of 2x is x squared plus some unknown constant. There's an information loss whenever you take a derivative. When you take a derivative, you're losing information on what the original vertical shift was. So that's why we say that the antiderivative of f prime of x with respect to x is f of x plus c. When I say go, I'd like you to say out loud and in unison, the antiderivative of f prime of x with respect to x is f of x plus the constant of integration. Ready? Go. The
antiderivative of f prime x
with respect to x
is equal to f of x plus the constant.
Yeah, you can say plus c, or you can say plus the constant of integration. That c is the constant of integration. Many people forget to write plus c, and so I do one thing. I only do this one time per year to just help you remember to write plus c. So many students say, well, the antiderivative of 2x is x squared, and they forget the plus c. How can I, as your teacher, help you remember to write plus c every time you take an antiderivative? Well, you don't want to miss this. If you're in the habit of when you blink, your eyes tend to be closed for like 10 seconds or more, then don't blink now. What I just did was I moved my body vertically through space to remind you that the plus c is the vertical shift in the family of functions. If you find yourself losing points on quizzes and tests because you forget to write plus c, just remember that guy who was shifting vertically through space. Let that be a visual reminder to you of what's going on. By the way, what if there's no prime? Well, then we write a capital F of x plus a constant of integration, where capital F prime of x, see, capital F means antiderivative, so it's capital F derivative of the antiderivative. They wipe each other out and take us back to the original F of x. So, if there's no prime on the original function, that's okay. We can find the antiderivative of f of x with respect to x. It's just capital F of x plus a constant, where capital F prime is lowercase f. Any questions on the notation that we'll be using here? Okay, our first goal here is analytical understandings of derivatives. And until we get to the dotted line, our format, our scheme, will be to take the derivative of a function, and whatever we get, we will then take the antiderivative of what we got here to see if it takes us back to the original. So, the derivative with respect to x of a constant is known to be 0. The slope of every horizontal line is 0. What is the antiderivative with respect to x of 0? Can someone think of a family of curves whose derivative is 0? So what would that be, class? Be a constant. Look, watching the movie forwards, the derivative of a constant is 0. Watch the movie backwards, it's an inverse derivative. Take the antiderivative of 0, you get the constant. But what about b? The derivative of b, is b a constant? Is there meaning attached to b? Have we had the spherical chicken talk?
No.
I owe you the spherical chicken talk, where we'll find out this uniquely human ability that humans have to attach meaning to symbols. The symbol b has a real constant attached, and the derivative of a constant is 0. Guess what the antiderivative of 0 with respect to x is? Just take a wild guess. Class?
C.
What?
B.
B? No, it's c. We use c to represent the constant of integration, not b, even if the original constant was b. Okay. So we got past that bump in the road. How about kx? The derivative with respect to kx, like could be 5x, 6x, 7x, the slopes of all those lines are k. So now, what is the antiderivative of k with respect to x? Write down what you think the family of functions is whose derivative is k. Then check in with the shoulder partner. See if you can find a shoulder partner who agrees with your answer. You need a family, a whole family of functions whose derivative is k. All right, who's got the family? Does anyone have a family a family of functions whose derivative is k? Yeah, Shara.
Kx plus c.
Kx plus
C.
c is correct. Any questions on how to get this family of functions whose derivative is k? Then finally, if the derivative of f of x is f prime of x, then we can say that the antiderivative of f prime of x with respect to x is f of x plus c. So that's a review problem. We saw that notation already. Any questions up to the dotted line? All right, now, beneath the dotted line, we're going to follow a different plan. Now what we're doing is taking the same function in both columns. In the left column, we'll take the derivative of that function. In the right column, we'll take the antiderivative of that function. So, for example, review. When it comes to scalar multiples, they come out front. K is not influenced at all. It's not phased by the derivative process. It just comes out front. K is out front. Take the derivative of f, you get f prime of x. Happily, the same is true for antiderivatives. A scalar multiple k just comes out front. So it's k times, you could think of it as the quantity, even though this I would not write down, I would just let this happen in your mind. You could write down k times the quantity, capital F of x, because the antiderivative of lowercase f can be represented by capital F of x plus a constant. But when you distribute the k, you get k times f, capital F of x. And k times a constant we just call it a constant. It's like the k gets absorbed into c. Constant times a constant is a constant. So I don't recommend taking the time to write this down. Just write k, capital F of x plus c, where capital F prime of x equals lowercase f of x. Makes a lot of sense. The derivative of the antiderivative gets you back to lowercase f. But the short version of the answer is what I have here in the red box. I just noticed that the camera needs to be pointed over this way just a little bit to get that in. Here we go. K, capital F of x plus c. Now, happily, the derivative of a sum is the sum of the derivatives. Same thing for antiderivatives. Good news here. This is going to be f prime of x plus or minus g prime of x. If you want to take the antiderivative of f of x plus or minus g of x dx, that's a plus or minus symbol, the answer is just capital F of x plus or minus capital G of x plus a constant. I mean, this has a constant, that has a constant, they glom onto each other and turn into some other constant. So anyway, the short version of the answer is to just say this, where capital F prime is lowercase f and capital G prime is lowercase g. Any questions on page 1 of our plunge into antiderivatives? Let's go to page 2. Now, on page 2, we're going to continue this theme of taking derivatives on the left, antiderivatives on the right. I mean, you know the routine. Derivative of x to the 4th is 4x cubed. Now, if you were to think of this as a two-part movie, two-act play, in Act 1, taking the derivatives, and here, I'd like you to look up here so you can imagine a play being acted out in reverse. The first act of the play is to multiply by the exponent. And then in the second act of the play, we subtract 1 from the exponent. Can someone describe to me what that play would look like if you watched it in reverse motion? What would the reverse of multiply by the exponent and then subtract 1 from the exponent be? What would it sound like if someone were describing that? Elijah?
Add 1, it'd be the exponent plus 1 divided by exponent plus 1.
Yeah, you would add 1 to the exponent and then divide by the exponent. That's what it would sound like if someone were describing it in reverse. And that's exactly what's going to happen here. If you're going to take the antiderivative of x to the 4th, you add 1 to the exponent and then divide by the exponent plus c. That's all there is to taking the antiderivative. By the way, if you don't believe it, then you can take the derivative with respect to x of your answer, x to the 5th over 5 plus c. Because if you do it right, then you should get whoever's in the canoe. X to the 4th is riding in the canoe. It's canoe is not an official mathematical term. The official mathematical term for the passenger in the canoe is the integrand. The integrand is the input to the antiderivative process represented by this canoe-shaped operator. So if we take the derivative of our answer, that should get us back to the integrand. Let's find out. The derivative of x to the 5th over 5 is 5x over. So 5x to the 4th plus 0. Sure enough, 5's cancel. It worked. Elijah's scheme of adding 1 to the exponent and dividing by the new exponent works. Here, you try it. Let's look not only at the derivative with respect to x of x to the 7th, but also the antiderivative with respect to x of x to the 7th. Try them both on your own. This is a good way to study calculus, by the way. Take any function. Ask yourself, do I know its derivative? Do I know its antiderivative? X to the 7th. Do I know its derivative? Of course, you know it's 7x to the 6th. Can someone tell me what the antiderivative of this is? What is the family of functions whose derivative is x to the 7th? Paul, you have it?
1/8 x to the 8th.
1/8 x to the 8th.
Oh, plus c.
Plus c. I think you could jump higher than that. Any questions on this family? So in general, what we have here is derivative of x to the n is n times x to the n minus 1. Antiderivative of x to the n is x to the n plus 1 divided by n plus 1 plus c semicolon n does not equal -1. There's a caveat here. We can't let n equal -1 because then we'd be dividing by 0. So let's look at the n equals -1 case separately. X to the -1 is 1 over x. Does anyone happen to know an entire family of functions whose derivative is 1 over x? I'm sorry? I think someone said it. Natural log of the absolute value of x. What's missing? What's missing? Plus c. You probably remember the day that we took the function natural log of the absolute value of x. We sketched its graph. Because of the absolute value, we had not only a branch to the right of the y-axis, but also to the left. And I asked you to just kind of guess based on graphing the derivative of that function, and you came up with a function that looked like it was 1 over x, and then we proved that it really was 1 over x. So that's why when n equals -1, it's natural log of the absolute value of x plus a constant. So, by the way, just review, the derivative with respect to x of 1 over x, which can also be written as x to the -1, is write down what you think it is and then check to see if we agree. I hope you're thinking -1 x to the -2 written alternatively like this. Any questions up through number 10? We doing okay? Swear, yeah, let's do fist to 5, where fist is no understanding whatsoever at this point, up to full understanding, ready, set, go. Fist to 5, where are we at right here? Okay, so I see 4s and 5s. Now's a good time to ask questions. If there's not full understanding, let me know.
Can you explain 10 again? Like, how do you get -1 over x squared?
For the derivative?
Yeah.
Okay, so the derivative of x to the -1, we multiply by the exponent and then subtract 1 from the exponent.
Okay.
So it's -1 x to the -2, which can be rewritten like this. Yes, Jack?
Can you explain the one right next to it?
This one here? Okay, do you remember the day where we said that the derivative of I wrote y there, and that might have been part of why you were confused. Do you remember when we looked at the graph of y equals the natural log of the absolute value of x? It's the absolute, it's the natural log function and the natural log function reflected over the y-axis. It's this red two-branch function. So you're okay with the graph of that? Notice how when you just try to sketch graphically the first derivative, the slopes are really steeply positive. So the y-coordinate of the purple derivative would be positive infinity, getting closer and closer to 0. Slopes are positive, sinking towards 0. Over here, slopes are negative, sinking towards negative infinity. So it looks like the derivative of natural log absolute value of x is 1 over x, which means that the antiderivative of 1 over x is natural log of the absolute value of x. Going this way gives us the derivative, reverse it, you get the antiderivative. Yes?
Can you explain again how you double check? Like up there.
Right, how I double check?
Yeah.
Okay, so like for example, this one right here.
Mm.
So x to the 5th over 5 plus c. So double check that. X to the 4th dx. If I think the answer is 1/5 x to the 5 plus c, but I'm not sure, I can double check by taking the derivative with respect to x of my answer. My answer is 1/5 x to the 5th plus c. The derivative of a sum is the sum of the derivatives. So the derivative of this term is 1/5 times the derivative of x to the 5th, which is 5x to the 4th. The derivative of c is 0. Upon cancellation of the 5's, we're back to x to the 4th, which is the integrand. So that's how we check to make sure that our family of functions really is the antiderivative of this. Okay? Yeah, Jack.
What would be like the antiderivative of 1 over like 5x?
Right. So if I were doing 1 over 5x, I would pull the 1/5 out front, and really I would just, dx. I would take 1/5 times the antiderivative of 1 over x dx. That would be 1/5 natural log of the absolute value of x plus a constant
What if
integration.
it's 5 plus x?
Oh, 5 plus x? Okay, then you'd have to come to school on Monday and learn about u substitutions, because you're not ready for that one yet, but that one we'll do Monday. All right, so u substitution. Let's go next to number 11. Now, these are where you're going to find out that these are really not 20-minute problems. They're not even 20-second problems. They might be like 0.2 of a second problems. I mean, come on, antiderivative of 5 is the family 5x plus c. Try numbers 12 and 13 on your own. Rapid fire problems, they just don't take much time at all. Check in with someone nearby on your answer to number 13. See if you agree on number 13. When you find someone who agrees with your answer on number 13, please raise your hand. All right, Cindy, go ahead.
X squared plus c.
Cindy got x squared plus c. Raise your hand if you agree with x squared plus c. Now, actually, you can check this. The derivative of this is 2x, so it matches up nicely. Any questions on number 13? Let's turn the page. Doing a great job, by the way. Moving right along. 3x to the 4th. Now, this one is pretty straightforward. We're just talking add 1 to the exponent and then divide by the new exponent. Now, sometimes this is going to be written as 3/5 x to the 5th plus c. But on number 15, before venturing into the calculus, I would recommend that you rewrite the problem as x to the -4th. So now when we follow that narrative, let's conform to the add 1 to the exponent and then divide by the exponent plan. We get this. Now, the answer in the back of the book will probably not look like that exactly. It will probably be rewritten either like this, which I have here in red, as negative 1/3 x to the negative 3 plus c. Or it'll be written as negative 1 over 3x cubed plus c. So either this or that are more likely to be the representations of the answer in a multiple choice setting. Also, on number 16, it's worth your time to rewrite the problem as 5 comes out front. It's a scalar multiple. It's unaffected by this elongated s. Rewrite square root of x as x to the 1/2. And then try to finish it from there. What's 5 times the antiderivative of x to the 1/2 with respect to x? It's best not to try to do too much in your head. Add 1 to the exponent, divide by the new exponent. But dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm thinking that 10/3 x to the 3/2 plus c is how the answer is most likely to appear in a multiple choice setting. Are we okay with this one? All right, give number 17 a go. And number 18, we're gonna make it a little more challenging. This last x, we're gonna make it x to the negative 1 right there. X to the negative 1. All right, so try 17 and the modified version of number 18. Are you remembering the plus c's every time? Who thinks they've got the answer to number 18? You say it, I'll write it down. Whether it's correct or not, it'll be kind of fun. Who's got number 18? All right, Will, go ahead and tell me what you have so far.
Actually, no, I'm still writing it down right now.
All right, well, tell me what you think the antiderivative of 3x to the 4th is.
3x to the 5th divided by 5.
Yeah, so we'll call it 3/5 x to the 5th. Keep going.
And minus 5x cubed divided by 3 and plus x squared.
Careful. N is equal to -1. So isn't x to the -1, isn't that the same thing?
I didn't see you change that.
So what would the antiderivative of x to the -1 be?
It's b0.
Well, but remember, that formula doesn't work when n equals -1, because we'd be dividing by 0. So instead, you have to remember, what is the family of functions whose derivative is 1 over x? Close. It's ln of the absolute value of x plus a constant of integration. Any questions on number 18? Yeah, check.
So is it for each, like, when you do it for each individual part? Is it adding c?
Yeah, if you wanted to show what's really going on here, it'd be 3/5 x to the 5th plus c1
Okay.
plus -5/3 x cubed plus c2 plus natural log of the absolute value of x plus c3. Now, a constant plus a constant plus a constant is a 4th constant, c4, but ultimately, since it happens problem after problem after problem, we just do the combining of constants in our head, and we just say, there's gonna be a constant of integration at the end. But yeah, that's an excellent point. That's what's actually going on. Thanks, Jack. Now, antiderivative of 0, this is review. We've done this one already. What is the antiderivative of 0? Can someone think of a family of functions whose derivatives are, raise your hand, anything you know? Shriana? C, the constant c, not b, not a, c. We use c traditionally as the constant of integration. Now, number 20, it's scary looking. Can you imagine you're canoeing on the lake and some canoe comes up beside you There's no one in the canoe. It's an empty canoe. You're like, I mean, it'd be like driving on the highway and you see a car next to you. It's an empty car. 55 miles an hour, 80 miles an hour. There's no one in the car. One of these crazy new self-driving canoes. Just a terrifying thing to even begin to imagine. But you know what though? It's a ghost. There's an invisible canoe occupant. It's always the number one. If there's, it's kind of like x squared. What's the coefficient of x squared? There's an invisible one there. It's 1x squared. So really, when you see antiderivative of a ghost with respect to x, that's really the number one. And so, in fact, if you want to actually show work, which I don't expect anyone to show work on this, but it's really 1 times x to the 0. If you want to use the formula, because then add 1 to the exponent, divide by 1. Anyway, the point is it's x plus c. I'm not asking you to show any work. That's what's going on in your imagination. The family is x plus c. Any questions on number 20? The TI-89, we used to have a TI-89, so we have a computer algebra system. The TI-84 does not, so let's just go to the next page and check this out. Now for trig integrals, you remember the cycle of length 4. Back in a previous chapter, we looked at this cycle of length 4. We developed it by taking f of x and calculating its derivative. Like sine of x has a derivative of cosine x. Now let's bring that down. What's the derivative of cosine x? Negative sine x. What's the derivative of negative sine x? Negative cosine x. What's the derivative of negative cosine x? We're back to the beginning. So then we start over. Cycle of length 4, sine x, etc. So when we talked about the cycle of length 4, it was for taking derivatives. We always went on this list right here. We went down. Sine is cosine. Once we get to the bottom, we wrap up to the top. Derivative of negative cosine is sine. Derivative of sine is cosine. So let's go down and wrap around. So derivative of sine of x is cosine of x. Derivative of cosine x is negative sine x. When you're taking antiderivatives, you go up on the cycle. I'm talking about the cycle in the red box. You go up and then wrap around when you get to the top. So using our strategy, it's a great strategy to review for tests. Take a function. Do I know its derivative? Do I know its antiderivative? Do I know the antiderivative of sine x with respect to x? Well, if you utilize the cycle of length 4, sine of x, that's right at the top. So wrap around to the bottom. It's got to be negative cosine x plus c. And if you don't believe it, take the derivative of negative cosine x. The derivative of cosine x is negative sine x. So the derivative of negative cosine x would be negative sine x. Oh, sure enough, it works. So we found the family. Would you please try to do number 24 on your own? I'd like you to think, what is the antiderivative of cosine x with respect to x? Find the family, use the cycle of length 4, but not in top to bottom fashion, in bottom to top fashion. Who thinks they've got the answer? I'll take a volunteer. Anyone think? Okay, all right, Mia, go ahead.
Sin x plus c.
Well done. Sin x plus c is the family of curves whose derivative is cosine x. Now, you need to know that you do not know all of these. I mean, we know derivative with respect to y of tangent y is secant squared y. But we do not yet know a family of functions whose antiderivative is tangent y. So if you don't know that, you might try to do the problem and waste a lot of time. That is TBD, to be derived later. We don't know it yet. We know that derivative with respect to theta of secant theta is secant theta tangent theta. But we do not yet know a family of functions whose antiderivative is secant theta. Same thing with cotangent and cosecant. For review, go ahead and write their derivatives. You can write the derivatives over there. Watch out for the letters of the alphabet they use. This one is negative cosecant x cotangent x. All right, so some of these we don't know yet. But by the way, in terms of applications to physics, keep in mind that there is something about the derivative that talks about rise over run or slope. So slopes of tangent lines are great applications for the derivative, rise over run. How about f of x times dx? It does look like f of x times dx, even though that's not how we pronounce it. We don't say what's s f of x times dx, but in reality, that's like f of x, that's like a function, it's like the height of the golf ball. It's really length times width is what it is. It's like the height of a rectangle. Instead of rise divided by run, it's like rise times run in a very significant way. It's really, you could think of it as height of a rectangle times length, or rise times run. Either way, it's going to give you area. So the antiderivative is going to have applications later on in area problems. The derivative has applications in slope. That's just kind of like a physics preview of where this is going. But for now, let's go to the next page and wrap up a couple of problems before we go. Now, there are some trig integrals that are pre-cooked. Like, for example, this one, they cooked it up to watch a movie backwards. I mean, doesn't it make sense to you that cosecant x plus c is the family of functions whose derivative is negative cosecant x cotangent x? However, this one, it can't be done. I mean, we can do it when it's pre-cooked, but not like that. However, we can do number 31. Surprisingly, number 31 is deceptive because this is an x and that's a y. It's just like antiderivative of 5 dy. If these letters don't match up, then treat this as a constant with respect to that. So just like antiderivative of 5 dy is 5y plus c, the antiderivative of cosecant x dy is cosecant x times y plus c. Cosecant x is treated as a constant because the letters don't match up. This is just review. We've already done this problem. Kx plus c. Try number 33. See if you can handle letters of the alphabet other than the letter X. And I want you to know that number 34 looks like it cannot be done. However, upon closer inspection, tan in one section, tangent squared x plus 1 equals secant squared x. So, can't we rewrite secant squared x as tan in one section? So tangent squared x plus 1 equals secant squared x. We can rewrite that as tangent squared x plus 1 dx. And we know this one. We know a function, secant x. Its derivative is tangent squared plus x plus c. So some of these we tan in one section. And likewise, tangent squared x is secant squared x minus, sorry about that. I was thinking number 35. Number 34, no. We don't know because the derivative of secant x is not tangent squared. The derivative of tangent is secant squared, but this one is TBD. So I was ahead of myself. Just hang with me here. Just let's wrap this one up. 34 cannot be done. We don't know that one. But we can rewrite tangent squared x as secant squared x minus 1. And the antiderivative of this is tangent x derivative, See, I was rushed. And so I stopped thinking clearly. But 34 can be done, can't it? What is 34? It's just tangent x plus c. So, tangent x plus c is this one. I was using tangent squared x. I was rewriting that one when I didn't have to. 34 was straightforward. 35 looks like it's not straightforward, but it can be done. So, the homework is on the syllabus. It's due Monday. Have a good weekend.